Let this recording start. Okay, fine. So today we going to discuss regularization and some probabilistic concepts, and then I introduce you maximum likelihood, right? So just a quick recap what we were doing in last year classes. We were discussing about what is overfitting and what will cause what is generalization underfitting. Then we come up with how you will detect overfitting. Then we said that we discussed about what are the parameters and how the norm of the parameter grows as we fall into the overfitting. That was a really big discussion that we had in last class. And today I will just touch that same concept and I will introduce how to tackle the problem. So if you remember, we were saying that when you just try to use heavy models like very powerful models, for an example, the desired model was m equals to 3, but we were discussing just just uh, just a moment. So we said that as you grow in the capability for m equals to 9 or 10, then your model will try to fit for every data set, right? And in effort of fitting to every data set, your norm will grow. Norm will grow means every value in the parameter w0 to w9, it will grow in size. And we had get a intuitive feeling of what do you mean by bigger norms, right? It means that it will be more ziggy, right? And you will get very rapid turns in the curve if you are fitting a polynomial, right? So we had this discussion, and then we were saying how to tackle that. And then I said that okay, if you just somebody asks you to just you can't go beyond some capability, all right? So then I introduced you constant optimization problem. So I said that if somebody says to you that the norm cannot be bigger than one, right? So norm can be of different type. So norm is a very general term. So norm can be norm one, norm two, norm three. So I will be specifically when I say loosely that norm. So if I don't mention it, so it will be loosely Euclidean norm. Euclidean norm means you are squaring the terms and taking a square root of the sum of those terms, right? So if you take norm 1, so it will be like in 2D it is a square. So I want to say that if there is a constant that you cannot go beyond norm uh, of size 1. So if I want to write like this, so it is the norm of a w, the norm of a w. So w is a vector here, right? So I'm taking just w. Though w is a vector, whose dimension, which dimension is from w0 to 9, right? So this is the big vector. So I'm saying that norm 2, right? So writing this way, we is saying that we are taking norm 2 and it should be less than or equal to 1, right? So when you write like this, I hope this is not getting clipped, right? Which I'm showing you right now.
Yes, sir. Visible.
Can you see this less than 1?
Yes, sir.
Okay, fine, fine. So it means like norm of w should be less than or equal to 1. And just to feel it intuitively, I said that let assume that w is of two dimension, w0 and w1. It means I'm talking about line. So this is w0 and this is w1 on y-axis. So it means you're talking all those lines whose intercept and slope collectively fall into this circle, right? And you cannot go escape this circle. So this is a constant optimization problem. When you do it, it means you cannot have a slope which is having 100, right? You cannot have 100 slope because 100 slope will fall somewhere out of the circle, right? And here if you see this point is nothing but 0, 1. 0, comma 1. It means intercept is 0 and slope is 1. So this is the maximum line that you can get, right? Intercept in 0. If you talk about this point, it means 0 minus 1. So the maximum line that you can go get is minus 1, like this, right? Then you go to this point on the circle. It means this point is 1 0. It means you are talking about that intercept is 1 but slope is 0. So you are talking about intercept is 1 and slope is 0. And if you talk about this, it means intercept is minus 1 and slope is 0, right? So this is this point. So it means you're talking about this point. So you take all those lines which fall in between these categories, and you're trying to fit your data set, right? So then you will not get very those lines which are having 100 slope, right, and 100 intercept, right? So you are not taking those lines which are having minus 100 slope and minus 100 intercept. So they're just not considering those lines for your data set. You are considering some specific lines which fall into some category. So just to show you intuitively, I'm taking an example of line, but if you come into a 9 dimension, so you can imagine like for every corresponding parameter W0, W1, W2, you cannot have a value greater than something. That something could be constant. And for specific example, I have taken that all together you cannot grow more than one in Euclidean. Right. So the moment you understood this concept, you please stop me if you don't understand this concept. So we can go for discussion. So the moment you understood this visually or intuitively or geometrically, that okay, you just to avoid overfitting, the you should not grow in norm of a parameter. That's why you just put a constant on that parametric norm, and once you put a constant, you will not have that ziggy turns. So how to put it in a mathematical form so that you can implement it and find out a solution, right? So uh, so to do that, you had this error function, right, which we had discussed before. So this was an error function, and I said that this is your line or curve, right? This was that curve, and this is your values in a given data set. So it means like the curve is, let's say, line here, and these were the data points. These were the data points, right? So now you say that what is the difference between your curve and a line on a specific x, and then you square it and sum it. This is what we had learned before, and we were composing an error function. But now, because we want to introduce a regularization here, we said that okay, you want to minimize these errors. If you don't put constant, then your line will get a twist here and it will go through here, right? Your line will get a twist here and it will go through here. Somehow your line will get twist here and it will go through here. So it will try to go through every point in a data set just to minimize the error. If you don't have any constraint, right, and your curve will take any turn, any sharp turn, because you don't have any constraint over w's, and w will be controlling the individual terms, right, of that polynomial. So quadratic will go any high, cubic will go any high, so there was no constraint. Now, because now you know that geometrically how to control these sharp turns in the curve, you are adding one more constraint to the error function, and you say that okay, you want to minimize the error, but side by side you have to put a constraint on the norm of a w, and it should also not grow. So see, very clearly strike, there's a but I think somebody has switched on the mic. You can please mute your mic. Please check yourself. If you don't have any query, please mute it. So if you have query, then you can please go ahead and ask me. So there are two terms here in error function. This is first term, which we had originally, right? And this is looking for try to minimize the distance between your training data points and your curve. This is the first term. You, to minimize this first term, you try to take very sharp turns so that your curve will grow through every data point. But what will happen just when you try to minimize this first expression, your norm will start getting bigger and bigger. Then you introduce this second term, just ignore this lambda by 2 for now. Then you introduce this second term, norm of w square, right? So it means your Euclidean norm will grow, But because it is a part of error function, you want to minimize it collectively, right? So error as a whole, you want to minimize it. So you want to minimize these both terms collectively, because the sum you want to minimize. If you minimize the first term, automatically your second term will grow, because it will try to go through every data point and will take ziggy turns. The moment it will start taking ziggy turns, your norm will grow. So if the norm will grow, it is also a part of error function, and you will try to minimize the error. So it means you're trying to minimize the norm. When you try to minimize the norm, this first term will grow then, because now your curve will not grow to every data point. So there is a trade-off actually. Once you minimize the first term, the second will grow. When you minimize the second term, the first will grow. And this is a trade-off, right?
So what is a Ziggy term?
Ziggy term means, like for an example, there is like a polynomial is w0 plus w1x plus w1x square. You just refer to my previous slides videos which I have told you. So
Okay.
if your polynomial has to go to some every specific data point, then the
Hmm.
value of these w will start growing, right? So Ziggy term means, like if there is 2 points here and your polynomial is coming from this side, so first it will try to go through this point, and if you don't have a constraint, then it will try to take a very short turn to go through this data point, right? And if you have another data point here, it will again take a very sharp turn and try to go, sorry, and try to go this through this point, right? So this is what I mean to by very sharp and ziggy turns.
Okay.
So right, so and why the result of these ziggy or sharp turns is that your norm will start growing, and because you have a constant on the norms, then it means you need to like take a control of it. I hope this is a you have better understood the intuitive terms. What is a trade-off between these, why there is a trade-off between these two terms, right? It is a very quick takeaway, and you should remember it. Now, just to tune like how much you want to control the capacity of a model, you are adding one important parameter. And because it is because we have to distinguish between these two different parameters. One is the parameter of a model, which are these w0 to wm, and this is some hypothetical some additional parameter which I introduced to my error function, which controls some complexity, but it is not directly related to this model. So we say that this, though this is a parameter, but it is a parameter of a parameter. So we say it's a parameter of a model. Try to come fit it. So it is, we call this kind of parameter of a parameter as a hyperparameter. So this is a hyperparameter here, because lambda will control the complexity of a model. Though you start with 9, let's say m equals to 9, and if you put lambda equals to 0, right? What is the effective capacity of a model? Can anybody tell me? If I say lambda equals to 0 and m equals to 9, what is the effective capacity of my model? My lambda is 0 and m equals to 9.
Then there is no constraint as such.
Very nice. So there is no such constraint. So it means I am not doing any regularization at all. But if I took lambda equals to infinity, then what will happen?
Highly constrained.
What will be the result of a model then? Though I have started with m equals to 9, what will be the constraint? Like what will be the effective model I will get? What is the power of that model?
Sir, a line.
M equals 0.
Exactly. So it is like m equals to 0, and you're putting every constant. You don't want to grow in any parametric dimension. And that's hence you will be try to reduce this infinity. And in effort of reducing infinity, you are reducing this w as much as you can, and it shrinks to a 0. So all the w, though at first, if you, it means you want just this point on the parametric space, right? If you are in 2 dimension, and the moment you start relaxing your lambda, it means you're growing you are expanding your parametric solutions, right? How many of you understood this statement which I just said? The moment you start relaxing your lambda, you are actually growing in a feasible solution space. Can you quickly type yes or no for this? The moment you start relaxing your lambda, you are actually growing, you are expanding your solution space where you're looking at solutions, right? It is very, very important, crucial term in terms of machine learning. If you understand this concept, it is really, you need something crux about the what when you claim that you know machine learning. Okay, very nice, very nice. So if you don't understand, still no way to no reason to get panic. You just discuss among your friends, and if it is required, you please let me know. We will see it. So now you know what is a tool in your hand, and this tool is known as regularization. So the moment you start controlling, you fixing a value. So nobody in the world come and tell you that lambda value should be 0 or it should be infinity. Now you have two problems at your hand. First, you were looking only the value of W0 to Wm. Now additionally, you have one more hyperparameter lambda, which you need to know, like what should be the value of a lambda. So in advanced machine learning, there are ways to find out lambdas also, and I will introduce to you. So I will definitely introduce to how to get a value of a lambda using Bayesian learning and all. So once I find out, like you start getting the concepts, I will introduce that thing also. For now, I will stick only to find out how to find out the values of parameters, not hyperparameters, right? So we will be assuming that we will be doing some tuning to a hyperparameter. First, we'll put lambda equals to 0, then lambda equals to something something. And here is the this intuition. If you take log of lambda equals to minus infinity, the effective value of lambda will be 0, right? Because it is a log of a lambda. So log of lambda is minus infinity, right? You know that log curve is something like this, right? So it is, so for log 0, for lambda equals to zeros, so it will be minus infinity, right? So it is like you don't have any constraint. If you don't have any constraint, the value of those w's will be same what we had here, right? So these values are same. It means we are not at all doing any regularization here, right? So if we are not doing in regularization at all, we will get the same solution, right? Now, if you say lambda equals to 0, log of lambda equals to 0, it means you are putting lambda equals to 1, right? So you are talking about this point. So when you are talking lambda equals to 1, it means the error function effectively will be, so this lambda will be 1 now. So it is half, right? So you are taking half of W. When you take a gradient of it, this square will get cancelled with this 2, and you will get a nice solution, analytical solution. So lambda equals to 1. When you put it, you will get this, your error function will reduce to this form, right? And meanwhile, some lambda equals to minus 18, it means you have some effective value between somewhere here, right? So you will take some value less than of lambda, less than 1, and you just tune it. So you see that for this value, your parameter W will be not as big as this was when it was having no regularization. So it means the effective capability. So if you are using m equals to 9 and you would have get this kind of function, when you start using your regularization, the effective function will be somewhere like, it will be less ziggy and in turns, and it will be like more smooth, very smoother, and near to like a linear function. The more you get a constant on it, it will get linear and linear in form, and somehow it shrinks to 0 in a norm, in the parametric space. Fine. So then if you see this graph, what it is trying to show you, that the moment you start increasing your lambda, right, it means your effective regularization will come into a play. It means you are not using very powerful model to fit to the data set. It means your training errors start getting high, because training your curve will not go to the every training data set. It means your training errors start getting high. But the good part is, now the approx generalization will be good. So whatever your training error will be, your testing error will also be almost very same to the training error. But if you are here and you are not using any regularization, your training error will be 0. But the generalization is very bad, because whatever the approximation for training error and testing error, there will be a huge gap between them, right? So the desired solution is you will get less training error and less testing error, and they should be almost same. So somewhere this part is desirable. So here training error is less, right? And testing error is very close to the training error. So it is what sometimes desirable to that.
So are these values fixed or is this for any particular set?
No, no, this is just for that same example what we had taken, right? Just we use the data set from a sinusoidal waves and there were 10 data set. So this graph is for different lambdas they have put and try to fit the model for every lambda and they plot it. And once they plot it, they found out that the generalization keep on improving the more you regularization you do. But the more regularization will result into a less powerful model. It means the training error will be high, right? It means it is under going towards the underfitting situation. So if you do lambda equals to infinity, right, then it will be like totally underfitted situation, and you are using a wrong model to fit the data set, which is very very less powerful. Any other question?
Sir, if in this case m is equal to 3 and m is equal to 9 with regularization, which one will be better? Like since m is equal to 9 with regularization is more generalized now.
Right, very nice. So when you take m equals to 9 and you put regularization, somehow effectively it is m equals to 3, right? Because the moment you start putting constant of regularization on the error function, those its capability or power will get reduced. And it start from m equals to 9, it will start getting dropped towards m equals to 0. So if you tune your hyperparameter and if you tune it well, then though you are using m equals to 9, but if you are using right value of a lambda, you will get the same effectiveness when you will be using m equals to 3 without regularization, right? So somehow regularization will give you a control of using very powerful models without going into the region of overfitting when you just start putting more constant on lambda. Anybody else? Anybody have any question?
Sir,
Fine. Yeah.
sir, ESD pass, due to regularization, can some parameters get reduced to zero?
Yes, it can be. So there are different type of regularization. L1, L2. L2 means Euclidean when you put a norm over 2, and when you do norm equal to 1, it means rather than taking Euclidean norm, you just take absolute value of every dimension and take a sum, right? So in that way, there you are doing some sparse the solution. You want to find out a sparse solution. So that parametric norm and where norm equals to 1, you will be getting some dimensions reduced to 0 and some dimensions will be effective, having some effective value. So though there are 100 dimension, out of 100 dimension there can be 10 dimension which is having some values and 90 dimension can shrink to 0. So it depends upon what kind of norm you are using. So if right now I'm telling you norm 2, so it will uniformly try to shrink every dimension. But if you take norm equals to 1, it will shrink some dimension absolute to 0 and some dimensions will be effective. So right now let's get stick to this norm 2. And if you ask me what will happen if I could start increasing my lambda, then it means it will shrink every dimension somewhere and it will try to smooth the curve.
Okay.
Anybody else have any question?
As a follow-up to Rahul's question, that would mean that using m equal to 3 is more efficient than using m equal to 9 with lambda, right?
Come again, what is that?
Um, so if, as you said that if we use m equal to 9 and give a proper value of lambda,
Mm-hmm.
that can be as efficient as using m equal to 3 without any regularization, right?
Right, right, exactly, exactly. But we have no way in the world to find out which is the right model to use, right?
Right.
So ideally, Rahul question is right, but
Hmm.
practically, I will never get to know that the right model was m equals to 3. So I have to go for higher models, right? m equals to 20 or m equals to 50, and then I will start tuning my parameter, hyperparameter lambda, because I don't know what was the true function at that time. So that was what I said.
Okay.
Fine. So I hope that this give you a better insight of like what is regularization. Okay. So let's continue now for the next. Okay, so now I want to go deep dive into this probabilistic theory. I have already instructed you to just go through these basics of probability, because if I try to teach you probability, though I can do that, but it will not give you that intuitive sense of it. So you just go through this section on your own, and there are some numericals given it. Just do it by hand, and you will find out insight. Once these concepts will be required, then I will be touching it, and you will be getting more insights of it when you know these things, right? uh, am I connected? Just because I got a call here, right?
Yes, sir.
Yes, sir.
Fine. So this is now so in this you just go through this section of 1.2 by PRM and by Bishop. Now this is probability densities, and I hope that you know, you not hope, I know that you know all these things, and if it is required, I will be touching these parts. So I will be barely just discussing and let you know like what is required. So we will be using multivariate calculus here. Not to get panic, we will be discussing these also when it is required. So this is multivariate calculus, and all those laws which apply for probability density for univariate, it will apply for this multivariate also, right? Forever, this is what it is showing here. So in then you come for sum product and base rules. So you know what is this sum rule, and for continuous it is integration, right? If you integrate any density. So can anybody tell me quickly what is what do you understand by distribution? If I say that this is a distribution of p x comma y, so there are two variables involved in it, right? So if you just see this figure, so if there is a joint distribution and it is not continuous here, right? So I have discrete values of x and y. Let's say this is x equals to 1, 2, 3, 4, 5, 6, 7, 8, 9 till 9, right? For x, this is x-axis and this is y-axis. I have two values for y, and for x, there are 9 values. And this is a giant distribution, right? So when I say this is a giant distribution, it means I have a giant probability. For example, this window, if you ask me what is the probability of seeing x equals to 4 and y equals to 2 together, right? So what is the probability of seeing this window? So you will find it, you just, let's say you have a magical way to calculate it, but intuitively or geometrically, if somebody says, what is the probability of x equals to 4, right? So I'm writing small x. So I have assigned a value of x equals to 4. And what is a giant, and along with x equals to 4, you need to see y equals to 2, right? What is the probability for this? So it means you are just trying to see what is that chance that you fall into this box, right? So if you have some probabilities for every box, so there are, let's say, 18 boxes, right? In first row and second row there are 9, so there are 18 boxes. So what is the total probability that you fall in any of the 18 box? Quickly, anybody?
1 by 18.
What is the probability that you can fall in any one of the 18 boxes?
1 by
Sir,
18.
one, because it's sample space.
That is one, right? So because I'm
Yeah.
seeing in any one of that 18. So coincidentally, you may be quick in answering and you may get incorrect, but I know that intuitively it is very easy to understand. You just give a thought of it, and it is easy to digest. Okay, so this is a giant probability thing. And if you say that if this is a giant probability, it means that falling into a box will have some probability, some non-negative probability from 0 to 1. And when you sum all those probability, it will sum to 1, which is the rule of a probability, which says that if you just integrate over all the variables given, then the sum of the probability will be 1. And for falling in any of the box, either you have a zero probability or greater than zero, right? It is non-negative. And because it side by says that integration should be 1, so it means that any of the variable giant variable probability between 0 to 1, right? So you have done it hundreds of time, I know very well, because you have specific courses for statistics, machine, this linear algebra and probability. So uh, intuitively, just I want to show, just discuss it here. So if somebody says, okay, if somebody says that what is the conditional probability, marginalized. So there are two important concepts, marginalization and conditional. So if you ask me what is the probability of seeing y equals to 2 only, so you are not caring about what is the value of x. So though x can vary from 1 to 9 here on this axis, but you are not interested in knowing the value of x. You say that whatever, though they will be appear in pair, right? So they always appear in pair. So it is x and y. But you are saying, I don't care what is the value of x, but I am very interested in the value of y equals to 2. So if you ask me what is the probability you see y equals to 2, ignoring the fact that what the x is containing, then you need to sum all this row here, right? All these probability, you sum them up and you get this probability. So it is a probability of seeing y equals to 1. Similarly, this is a probability of seeing y equals to 2. So this is a marginalization. You are marginalizing over x. So you are not caring about x and you are summing all the probabilities of y. Similarly, you are marginalizing over y here. So what is the probability that x equals to 1? That x equals to 1, right? And you are ignoring the fact that what is the given value of y. So it means you are summing it column wise. So you are summing these probabilities column wise, right? And whatever the probability will come, you will get this distribution. So it is also a distribution. When you sum over now this distribution, you will again get 1, right? So first you have the sum up over column and then you have sum over rows. So it is not nothing but it is a distribution over all. You are summing over all the variables. First over x one by one, and then summing over, summing over y and then summing over x. So definitely you will get 1. So there are two type of marginalization. In the two-dimension case, x equals to either you are marginalizing over x or either you are marginalizing over y. So this is important concept we will be using again and again. And geometrically, this is how you can see it. The third important concept, the second important concept is conditional. So what is conditional? If somebody say, I know my universe is y equals to 1, right? I am in the world where y equals to 1. What do you think? Given y equals to 1, the x equals to 0. Can anybody tell me by seeing this figure, what is the probability of this probability of x equals to 1, x equals to 1 given y equals to 1? What is the probability? Anybody? 1 by
Sir,
7. Why Akash is saying 1 by 7. So my question is, just to make you again connected and understood, like using referring this figure, I am saying that my universe is y equals to 1. And now once I constrain my universe, that I am only standing and I am only able to see y equals to 1 values only. Now given that y equals to 1, what is the chances that you see x equals to 1?
It will be given by the leftmost bar on the figure over there.
Yes, there is a figure given, right? You can see blue dots, and also you are just considering the sample where blue dots are given. So what is the probability?
3 by total number of whatever things are
What
there
is the
in
total number? Why 3?
3 because there are 3 dots in the x equal to 1 zone.
X equals to 1, you are seeing 3 dots. Oh my God. So
Oh wait,
this
hold on,
is
that's equal to 0. My bad, my
this is
bad.
this is 2 and this is 9, right? So till 9. So on x-axis you are having 1 to 9 values. So I'm
Exactly.
saying y equals given y equals to 1.
Hmm. and
What is
x
the
equal.
chance that you see x equals to 1?
There are three dots in x equal to 1 and y equal to 1, right?
I don't know. You need to sell me. Anybody. Anybody. So it's people are writing 1 by 7 to 1 by 9. Other than this answer, anybody has an idea? Any idea? So I am able to see only this that world where y equals to 1. This is my constant world. Once I see I am standing in this world where I can see y equals to 1, I want to know like what are the chances that x is also 1 when y equals to 1. So it is a condition. First, I need to constrain myself that I can see only y equals to 1. Once I come into the world, then I find out what are the chances that x is also 1. Okay, let's see that. So let's see that.
3 by 32.
So my constraint is uh, y equals to 1, right? So this is my constraint. So I can see only this thing, right? I can see only this world, right? Given this x equals to 3, x equals to 1, this is the only thing that I am interested in. So it means you sum all these numbers which fall into the bigger box, right? And you take as a denominator and it will be 3 by this, the sum of all these dots, right? So it is something like the sum of all these blue numbers, right? And what if I say y equals to given what is the probability of x equals to 1 given y equals to 2? What is the probability?
0.
0. Very nice. This is the intuitive thing that you should see sharp at the moment, right? What is the probability that x equals to 4? So I will write it not to confuse you. What is the probability that y equals to 2, y equals to let's say 3, given x equals to 4?
0.
0.
0. Very good. And what is the probability given y equals to 2 and x equals to 9?
2 by whatever the total number of things are there in y equal to 2.
So I hope that you understood it, right? So that makes sense. So I'm saying that x equals to 9. So you are coming into this world, right? Then I said that, okay, y equals to 3. Oh, sorry, there is no 3. My question is wrong actually. So y equals to 1. You got my question, right? So this is y equals to 1. So now you need to just focus on this point, y equals to 1. So it is 0, right? So you just give a thought on it and try to understand the thing. And then you use these Bayes theorem. The Bayes theorem is just nothing but it is a joint distribution in two different sense and you're equating it. Okay, so let's try to grasp the things. What is an expectation? Quickly, anybody? You can unmute yourself. What is expectation? It is average, right? Yes, no. Can you type it quickly so that I can go get over this concept? Expectation is average. It is a generic term when we write in a continuous domain, right? So continuous space. So you can say that it is expectation. It is a theoretical concept, right? And entropy is one of the average, right? So you are taking average over what? So if you're taking a log of a probability and then you take an average, it is entropy. Similarly, mean is an average for discrete value, and KL divergence is these KL divergence is also an average uh, of what? So in general, you say average of this function, right? So this is in general, you try to take an average of some function value. So the function can itself be a variable, right? So you can say x px. So x px. So you are trying to see what is the probability of x. what is the probability of x, and what is the function here is it is an identity function. The function x is itself a function, but if you take x square, then it is moment 2, or if mean is 0, then it is a variance, right? It is expectation. You can take an expectation of x cube also, and you can take any function in general. So if you replace this function with log of the probability is entropy. So expectation in general sense, it is a average. Variance, you know what it is, like how scattered your data set is around the mean. Covariance means like how one variable vary from the along with the other variable, right? So if I say my can anybody tell me intuitively, if I have these points here, I have these 4 points, and I want to find out the covariance between x and y, right? Whether it will be a matrix or a single number.
It would be a line.
It will be a single number.
Single number.
Single number.
Yes, sir.
Are you sure? Covariance is between two variables, right? For two random variable x comma y, that their covariance is this, right? So I need you to just brush up these concepts. If you have any questions, just let me know. What do you mean by independent variables? Quickly, anybody tell me what is independent variables?
Change in one value does not affect the other.
Can you give me an example?
Uh,
So,
Birth rate in an X country and stock prices in some other country.
so yeah, you can hypothetically create any example when things are not that they are not related. The correlate. So if the variable are independent, then covariance is 0. Let's try to see it. So I say that this is expectation. I want to just generalize it in just I want to make it into a discrete case. So expectation, if you open the formula, it is nothing. The probability of x into y, probability of xy into the function itself. The function is xy, right? When I say they are independent, it means you can just expand it probability of x into probability of y, right? Probability of x into probability of y, because they are independent, right? And this is x and this is y, and the summation will be, the summation is because there are two variables, so that is over x and y. So when you just expand summation x over x and y, so you have a summation, two different expectation. If you just say x, so it is probability of x into x, probability of x into x, and when you just, there is another summation, probability of y into y, right? Probability of y into y, and it is nothing but expectation of x into expectation of y. And when you replace it, it is expectation of x into expectation of y, and it is a negative of it, right? So it will cancel each other, and then the covariance will be 0. So it means if there are two independent variable, then the covariance between those two independent variable will be 0. It means knowing one information doesn't tell you how the second will go. So you always remember that if there are two independent variables, the covariance will be 0 among them. It will be very important to understand, to remember. And I will give you intuitive feeling later when I will be taking this example, maximum likelihood. Okay. So now I came to a concept which will be like stick to you forever if you will be lying into this machine learning or deep learning field, right? You have to learn it, you have to understand it, and I will be giving a dedicated time on this concept. And because I'm less of a time now and time is over, so I will be starting this concept tomorrow. But I insist you to just go through these probabilistic concept, and please see all of you once, like what are the distributions, right? So you just try to understand intuition of our distribution, right? So then I will try to give you, and also just see what are the Gaussian distribution, both in bivariate case and univariate case. So you have two tasks here. you need to see what is Gaussian distribution. So the Gaussian distribution can be multivariate. So don't go for multivariate. You just need to see bivariate and univariate, right? So once you understand what are the distribution, obviously you understand what is a Gaussian distribution, and then you need to just have intuitive feeling what is a how bivariate Gaussian distribution look, how univariate Gaussian distribution look, and then I will start this my maximum likelihood with with a short discussion over probabilistic distributions. So I insist you to go through it, and if you have any question, you just raise me in this beginning of the class. So do you have any question now, or we should close the class? Okay. Thank you very much. Just drop your attendance and leave it. Thank you. But please go through these